Okay, we are doing section 3.5 on infinite limits. We're going to start with the definition of what an infinite limit is. And here I have two different definitions, one for when the limit is positive infinity and one for when your limit is negative infinity. So for an infinite limit, the meaning of having infinity as a limit is that you can make the y values as large as desired, more than 5 billion kajillion. All you have to do in order to make the y value as large as you want is to take the x value sufficiently close to the number in question that you're approaching. So if you take x close enough to the number, like maybe a is 2, if you take x close enough to 2, then your y values will just get larger and larger and larger. Number 2 is the same exact idea, only in the negative direction. We're getting huge, but with a negative sign in the front, so infinitely small. There's a very important concept to talk about right now, and that is the fact that infinity is not a number. If your answer to a limit is infinity, then that limit is non-existent because infinity doesn't exist. But we do like to talk about infinity as a notion, as an idea, as being as large as we want or as small as we want. And so if that's the case where you get infinity, then we want you to specify that the limit is infinity or the limit is negative infinity, but understand that that's not a number. Infinity doesn't really exist. Okay, so in example 1, I'm going to take the limit as x approaches 0 of 1 over x squared. And I'm going to do this example in two different ways. The first way is graphically. I know what the graph of 1 over x squared looks like. It looks like a hyperbola, but there are only positive pieces. And so I can see that when my x values get closer to 0 from the left, my f of x values jump up toward, they just go infinitely higher. And the same thing happens from the right. My x, y values go closer, higher and higher and higher as the x values get closer and closer to 0. And so this answer would be infinity. Okay, let me show you this analytically, which means by plugging in numbers. If x approaches 0 for 1 over x squared and you plug in 0, then you get a number divided by 0. And a number divided by 0 means that you're going to get some sort of infinity or does not exist as your answer. However, we're not sure at this point whether the answer is positive infinity, negative infinity, or does not exist, because you could have any of those three options. You have to do sided limits in order to understand this. So I'm going to break this down and first do the limit as x approaches 0 from the left. When I plug in a number very close to 0, but on the left side, I have to be careful there, because yes, I'm plugging in a number very, very close to 0. So close, it might as well be 0. But there are two types of numbers that are really, 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 really close to 0, but not yet 0. One of those kinds of numbers would be a negative number, like negative 0.00000001. And another type of number would be a positive number, positive 0.00001. And so you will get either positive infinity, negative infinity, or does not exist based upon whether your number that's really, really close to 0 is signed as positive or signed as negative. And so in this case, I'm going to consider a number that's 0, but not 0, just negative number very close to 0. So you could even fill in 0.001 if you would like, but I'm going to keep that as negative 0. And negative 0 squared is positive 0. Because if I take negative 0.00001 and I square that, I get positive more zeros 1. And so this answer is a positive answer. So that answer is positive infinity. If I take the limit as x approaches 0 from the right of 1 over x squared, I get 1 over a positive 0, and when I square a positive 0, I still get a positive 0. So this answer is positive infinity. And from the left and the right, I approach positive infinity both ways, from both sides. And that's why the answer to this limit is positive infinity. And you can see from the graph that from the left, the green, I approach positive infinity. And from the right, the blue, I also approach positive infinity. In this case, we say that this is an infinite limit. Now, example 2. Example 2 is the Mean Girls example. This is the question that the girl was asked in Mean Girls at the very end at the Mathlete competition, where the limit did not exist. And so let me answer this both ways again. Graphically, I know what 1 over x looks like. And when x is negative, 1 over x is also negative. And when x is positive, 1 over x is also positive in this hyperbola situation. Now, when I approach 0 from the left, my graph, my y values, shoot down to negative infinity. But when I approach 0 from the right, my y values shoot up to positive infinity. And so what's happening here is that this limit does not exist because I don't agree from the left and from the right. And so my limit does not exist. And let's do this analytically. So we're going to break the limit as x goes to 0 of 1 over x, which is 1 over 0, down into sides so that I can fully examine if the same thing is happening on the left that is happening on the right. So now if I plug in a number very close to 0, but not 0, therefore not neutral, but rather negative because I'm approaching 0 from the left, I get negative infinity. When x approaches 0 from the right, I plug in a number so close to 0, I might as well be 0, but I'm not 0. I'm actually positive, but very, 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 very close to 0. This makes me have a positive infinity answer. What's happening here is you're taking the number 1 and you're dividing it into pieces so very, very small that you have infinitely many pieces left. And that's why 1 divided by 0 is infinity. Think of 1 divided by point as many zeros as you can. 1. So this answer is 1 with that many zeros after it. It's huge, humongous. But then there's a sign associated with it. So when I approach from the right, I get a positive. When I approach from the left here, I got a negative. So this limit does not exist. I don't agree per side. Does it work out that from the left you get negative infinity and from the right you get positive infinity? No, it does not work out. No, that happened in this case. It does not happen in all cases. Please don't do that. I will make a question for sure in which that does not happen. Okay, so based on those graphs, you might have seen that one thing happened at infinite limits, and that was that we had what we're familiar with, the vertical asymptotes. So we have a new definition of vertical asymptotes, and it's a calculus definition. It's a calculus definition, a definition that involves calculus. So if x equals a is a vertical asymptote, then at least one of the 4 things happens. And that is that as you approach a from the right, maybe you get infinity. Or maybe if you approach a from the right, you get negative infinity. Maybe if you approach a from the left, you get infinity. Or perhaps if you approach a from the left, you get negative infinity. This can be summarized, all 4 of these, into the 4 possibilities that if you approach a from the right or the left, you get either positive or negative infinity. You don't have to get all of those. It would be impossible. But you have to get one of them in order for there to be an asymptote. Okay, so let's do an example in which I ask you to find a vertical asymptote. You know back from what we did in the first 9 weeks and from pre-calculus how to find vertical asymptotes. Vertical asymptotes happen to be when the denominator equals 0. Please be careful here. sometimes when the denominator equals 0, we have a removable discontinuity or a hole. Those are not vertical asymptotes. So the end-all be-all answer is not when the denominator equals 0, but when the denominator equals 0, there may be a vertical asymptote. So that's the way we look. That's how we start this. I'm going to factor. And x factors out of the bottom. And now I have two trinomials that both factor. This top factors as x minus 2, x minus 3. And the bottom factors as x plus 2, x plus 2. Oh, well, that's boring. Maybe I should change that minus 5x to a plus 5x. Let's do it that way. Now this will be x plus 2, x plus 3. Okay. And so, that's not that much better. Okay, so this isn't that much better. An x plus 2 cancels, but I still have another x plus 2 in the denominator. If this had been well, okay, so the way that we're going to answer this now is x equals 0 is a vertical asymptote, and x equals negative 2 is a vertical asymptote. Because those two x numbers, when plugged in, will make my denominator 0, but they will not make my numerator 0 once I've canceled. Ideally, this would be different than that. We'll do another one where it is. And so if you cancel, this is a removable discontinuity. But an asymptote supersedes the removable when you get that it cancels here. And to answer what the question for a vertical asymptote is, you have to do a limit. So let's do the limit as x approaches 0 from the right. And I have to get infinity as my answer of f of x. All right, so I'm going to recopy f of x, but I'm going to copy the factored version, the factored in canceled version anyway. So now if I plug in a number very close to 0, but just right as 0, I'll get 3 over a positive 0 times 2. This is a positive 3 over 0. Again, I have all positives, so this is positive infinity. That's why it's a vertical asymptote. I'm going to need to see a limit when I ask you to find vertical asymptotes. I'm going to need to see a limit when I ask you to find vertical asymptotes. Let's do the other one. And so here you would say vertical asymptote at x equals 2. Oh, 0, sorry. Let's do the other one, the one that was weird because it also canceled. The limit as x goes to negative 2. Let's come from the right. If I use my factored version, my factored and crossed off version here, then I get 1, because negative 2 plus 3 is 1, over negative 2 times, now so you have to think about this. What is a negative number close to 2 but on the right side of negative 2? So that would be negative 1.9. If I plug negative 1.9 in here, I get a number very close to 0 but positive. I got a number very close to 0 but positive. And so this is positive 0. So overall, the sign positive divided by negative times positive is negative. So I got negative infinity. Here's an example. I approached from the right side, but I got a negative infinity answer. So be careful there. Vertical asymptote at x equals negative 2. And we are done with this example. Here's another one. Determine whether the graph of the function has a vertical asymptote or a removable discontinuity at x equals negative 2. In this first letter A, if I do the limit as x approaches negative 2, my numerator does not factor because it's x squared plus 4. So if I plug in negative 2, well, let's do it from the right. If I plug in a number close to negative 2 but right of it, we just did this, maybe negative 1.9, I'll get a 0 but positive in the bottom. And in the top, I'll get 8. It doesn't matter how close, what side of negative 2 I'm on. I square negative 2, get 4, add 4, I'll get 8. So this is positive. But my answer here is positive infinity, so that means I have a vertical asymptote at x equals negative 2. On the second question, however, let's see what happens. If I do the limit as x approaches negative 2, this is a boring example. Let me change this. Let's make this x squared plus 2x. Now if I do the limit as x approaches negative 2 of x squared plus 2x over x plus 2, notice, wow, my top factors, my numerator factors here, x times x plus 2, the x plus 2's cancel, and I get an answer of negative 2. This is a removable discontinuity because a removable discontinuity at x equals negative 2 because my limit existed. There's still no value of the function at negative 2. You're never allowed to divide by 0, ever. But if you cancel, then you get a whole, not an asymptote. So a whole is a removable discontinuity. So this is an example in which we have a removable discontinuity, not an asymptote. And here's one more question for us to do. This is the last question. The limit as x approaches negative 1/2 from the right of this function. So let's just try to plug in and see what we get. Okay, so here I would get 6 times 1/4 minus 1/2 minus 1. So it's 3/2 minus 3/2, 0. And in the denominator, I get 4 times 1/4 minus 4 times negative 1/2, so that would be plus 2 minus 3 over 1 plus this is 0. I got 0 over 0. Work harder. So I'm doing the limit as x approaches negative 1/2 from the right. I need to factor this, right? And this thing does not factor nicely. 1 and 1. Those are my only options there. 3x, 2x. I want a positive x in the middle, so I should do plus 3x and minus 2x when those multiply together. And the bottom, I have to do 3 and 1. I'm going to guess 2x and 2x because of how the top looks. And I want a minus 4. So this would give me 2. This would give me 6. If I want a minus 4, this should be negative here to get me negative 6. Positive 2. Okay, so here's how this factors. Notice my 2x plus 1's cancel. So this is a removable discontinuity at negative 1/2. At x equals negative 1/2. But I can plug negative 1/2 in. In the numerator, I would get 3 times negative 1/2. That's negative 3/2 minus 1. In the denominator, I get negative 1 minus 3. So this is negative 2, negative 5/2 for negative 4, 5/8. There's my limit. So it was not an infinite limit. We had a removable discontinuity. This concludes our lesson.